the cloud. So we have, well, probability definitions, good place to start, I suppose. A branch of math that deals with the chance of an event occurring. All right. It could be multiple events too. You could have hundreds of events, but we tend to look at them one at a time. All right. That's the thing about probability. If you try to account for everything all at once, it gets a little overwhelming. All right. So we look at it sort of in a meticulous way, which can involve a fair amount of writing, which, if you're used to math classes of the function variety, like a college algebra class or pre-calc, and you might look at it and say, well, in those instances, I can get the answer just by looking at the problem, or I can just look at the picture on the graph and come up with the answer. Here, you kind of have to create a roadmap, right? Anybody who's got any experience with coding, like if you do any programming, you know what I'm talking about. It's like you have so many variables that are flying around that if you don't have a blueprint or a roadmap, at least in your mind, in some cases on paper, it doesn't always end up working out very well. All right. So anyway, an event is a collection of outcomes of a procedure. All right. So a quick example: you flip a coin. An event would be, either of the two outcomes, heads or tails. All right. But you could have multiple outcomes that are grouped together as one event. So if I roll a die, the six-sided number cube, like if you're playing, if a casino game, it's like craps, but I mean, even in Monopoly, you have dice, like a die is a singular of dice, if you didn't know. You could say the event is getting an even number, or in the case of rolling multiple dice, the event could be getting a 7, in which case you have 6 different ways that could happen. So, any of those 6 would be a success, but collectively they make up the event. All right, a sample space is a complete list of all possible outcomes in an experiment or activity, not necessarily what you want to happen, but what could happen, any possible event. All right. So that if you figure out the two things, how many ways the thing that you want can occur, and then how many ways anything could occur, any outcome, then you have the makings of a probability solution. All right. Notation is really important. P for probability, that makes sense. Later on in the course, we're going to call P proportion. It's the same thing. It's just different context. All right. So when you talk about a proportion or a probability, we're talking about really a ratio of successful outcomes to outcomes overall. All right. So I will actually make a note of that. Ratio.
Do you think you could do me a favor?
Depends on the favor.
Do you think you can, with all the notes that you put in the document, could you share that with me?
It's already available online.
Yeah, the notes, but not with the writing.
No, even with the writing, if you go to
Oh, it
class
is?
notebook, yeah, it's all there.
Okay, does it update after each class? Because I didn't see last week. I meant the week before. I'm sorry.
It should. Sometimes it takes a little.
Yeah, last week's for me. When I reviewed it after, the writing didn't pop up until a day later, so I would wait at least a day.
Okay, that's good to know. So about a day, but it'll all be there.
All right, thank you.
No problem. So ratio of successful outcomes to all possible outcomes. All right. So, it's kind of tricky because probability is a branch of math that deals with the chance of an event occurring. It's an entire subject area, but also we are looking for individual probabilities, kind of like when we talk about the course called statistics, but within the course, we actually find a statistic, so it's both the name of the course, which has its own definition, but also a subset of that. All right. A, B, and C are your specific events. So if I have P parentheses A, that's the probability of event A occurring. And then if we use a tilde, there's different notations that people use for not, but I use the tilde, and it's not like I'm a rebel. A lot of people use the tilde, but there's other notations that can be used. We just tend to stay away from it just for sanity's sake, right? There's a few different ways that we can come up with probabilities. Well, actually, before I get into that, I'm going to kind of steal my own thunder. So the probability of an event not occurring is equal to 1 minus the probability of the event occurring. And the reverse is true also. The probability of an event occurring is equal to 1 minus the probability that the event will not occur, right? That's what we call it's a complementary relationship. It's further down in the notes too, but it's a good, I mean, they're right here, so it's worth talking about it right now. Complementary relationship. All right. So if you know one, you can infer the other. All right. So if I tell you that the probability that I'm going to win in a particular game of chance is 1 out of 20, that means that there's 19 out of 20 ways that I could lose. All right. And usually the probability of winning has a relationship with the amount of money that you stand to win if you win, assuming you're talking about a game of chance. You've heard the term long shot before. That long shot is an outcome that's not very likely. So if you hit on it, it pays more, right? So I forget what it was. I think I know what the bet was, but I can't remember what the payout odds were. So I'm just going to make up. So I think I know. So back in, I think it was the Giants' second Super Bowl win in the last 20 years, the one in Indianapolis, a person posted online their winning ticket, that they placed a wager that the first score of the game would be a safety. All right, so that's a pretty unlikely outcome, and they bet it was 1,000 to 1 because it's not a very likely outcome, but they bet $1,000. So they got $1,000. All right, so ton of money. So that's what, $1 million with 6 zeros. So, I mean, I don't have $1,000 to be betting on anything. I don't even have like $10 to bet on anything. It's kind of my philosophy, and so it's tricky because not everybody's like this, but I work hard for my money, so I'm not going to just take a chance that I'm going to lose it all in one shot, without really any kind of guarantee or certainty. Right. So you could figure out probabilities using experimentation, a formulaic approach, or estimation pattern recognition. When you get into things like games of chance, oftentimes you're living in the world of experimentation and estimation pattern recognition. All right. Because if you know the probability that, let's say, I'll keep it simple, like red would be the outcome in a game of roulette. Yeah, it's not quite 50-50. It's 18 out of 38. That's the probability that you'll get red. So maybe you place a wager on getting red. But if the last 10 times the wheel was spun, red came up, you might be thinking, well, what are the chances it's going to come up again? It's not very likely. Right. And that like getting a stretch of the same outcome, or a streak, or a run is what we call it, is not very likely. So you might switch and bet on black, also 18 out of 38 probability. Right? Just because you recognize, well, black hasn't come up in a while, and it has to come up roughly 18 out of 38 times. You're not there all day watching the wheel get spun, so you don't really know what the breakdown is. At the end of the day, it should all even out, but maybe you're in a stretch of time where black hasn't come up in a while, so you're going to bet on black, or maybe red hasn't come up in a while, so you're going to bet on red. Those are things that you would get by estimation and pattern recognition, but also you can experiment. Like if you have unlimited funds, you can be like, oh, let's see what happens if, but that's not really very practical. All right. The simple cases, you flip a coin 200 times to get an idea of what the probability of getting heads is, right? That's opposed to like flipping the coin once and saying, oh, you get heads every single time because you flipped it the one time and you got a heads. Maybe you flip it 3 times and you get heads each time. Yeah, it's confirmed. Every time I flip a coin, I'm going to get heads. But if you flip it 100 times, you're going to get pretty close to 50 heads, 50 tails. It'll all balance out, right? Unless it's a trick coin, it's always a possibility. Seen that before. The coins are 2-sided, but both of them have the heads on it. So, just be aware of that as a possibility. I tend to keep things fair when I make questions. So a fair die, a fair coin, and so on. Your basic probability rules. We'll get to formulaic approach. That one's the most straightforward or the most complicated, depending on the nature of the situation. But the basic probability rules are really the kind of the foundation of everything that we do. Right. So your probabilities can only exist between 0 and 1. When we work with probabilities, we stay in decimal form. Right. They can be represented as fractions or percents, but decimals are usually the way to go. With the numworks calculator, actually most calculators now, they'll give you both the fraction and the decimal. So you really have kind of a lot of wiggle room. So for example, if you have a probability, let me go into calculate here. That's 1 out of 6. 1 out of 6 is pretty precise. I mean, it's exact. You'd have to round the decimal for it to work out, to put an answer down on paper, 0.167, which creates a little bit of inaccuracy. Right. So depending on the type of outcome, you may choose, or probability, you may choose to go fraction versus decimal. But historically anyway, people have found themselves doing working with decimals mostly. All right. So let me highlight it in a different color. This is very, very important. 0 is impossible. 1 means it must happen. All right. So just a little explanation on that. When we say something is impossible, we say that it's not the case that it didn't happen. It's the case that it could never happen. All right. So if I say you're flipping a fair coin, what's the probability of getting a heads? And you say 1 out of 2 correctly, or if I say probability of getting tails, 1 out of 2, that's correct. All right, 0.5 in both cases. But if I say you're going to flip a fair coin, one side is heads, one side is tails, what's the probability of getting green? There's no side of the coin that says green, unless one of them's painted green, but I'm saying it's a fair coin. So it's a regulation coin, nothing out of the ordinary. Green wouldn't be an outcome. Right. So I would say that that's a 0 probability. All right. Now, if I say you're flipping a coin, 2-sided fair coin, heads on one side, tails on the other, what's the probability of getting either heads or tails? Well, those are the only outcomes that you could get. No matter how many times you flip it, you're always going to get one of those 2 options. So that would be a probability of 1. All right. We'll get into the ands and ors a little bit more down the line, but that's just a very brief example. But it is pretty important. So anyway, complement rule, probability of A plus the probability of not A. This goes back to what I was talking about up here. Probability of A plus the probability of not A is equal to 1. That makes them complementary. And then this is what I hand wrote, but it's not in context here. It was in context up there. All right. So let me just take you through an example. Given a multiple choice question with 5 choices, what's the probability of getting the correct answer by guessing? All right. So we're going to define 2 events. Let C equal correct. let that not symbol be incorrect. All right. Just because it's listed with A's here doesn't mean it always has to be an A. You could say P of F. It really doesn't matter what's in there. Outside of this expression is always going to be P for probability, but inside it's whatever you're calling your event. All right. So we want to know the probability of getting a correct answer by guessing. Well, multiple choice question with 5 choices, we're going to assume that only one of them can be correct. The others are incorrect. It's just a typical multiple choice question. It's not a multiple selection, check all that apply. Didn't say that. It's a multiple choice. All right. So you have a 1 in 5 chance, or you could say 0.2. All right. If I want it to be incorrect, which I wouldn't, but in the event that I do, the probability would be, well, there's 4 ways you can get it wrong out of 5 overall, 5 choices. That's a probability of 0.8. All right. So the complement rule tells me that if I take, let me get a lighter color here. If I take this probability and add to it this probability, I should get a 1. So probability of C plus probability of not C would be equal to 1. That's the complement rule. All right. So I could test it out because I know what the probability of getting a correct answer would be. And I know the probability of getting an incorrect answer. Add them together, I do in fact get a 1. So this is verified. Okay, so we know that it's correct. Yeah, it's a pretty straightforward concept. I mean, we're going to do stuff with it that'll make it a little trickier, but yeah, it's not terrible. If I tell you the probability that it's going to rain tomorrow is 70%, 70% chance of rain, and then I turn around and say, what are the chances that it's not going to rain? Well, that's the other 30%. And so, there is some gray area, but that's a pretty straightforward example. I've had people say, well, what if it snows? I would say, well, is it raining? No. Okay. So I'm still right. It's just how it goes. There are situations where you do have gray area, and we got to be careful about that. We call that overlap between the different events. We use cards mostly to address that. I have a little blurb down here just talking about rounding 3 significant digits. It's the way we've been rounding all along, so it should be fine. But there's another little capsule summary just so you have it, right? Sort of kind of reinforcing that, yeah, we're still going to be rounding that way. If you're nervous about rounding, you could just stay in fraction form, all right? Because I know rounding can be tricky. Even if you're comfortable rounding, sometimes you just accidentally round incorrectly, and you don't want to lose credit for that. So if you want to leave it in fraction form, you could do that. This whole page here, page 22, is really just reference material, right? So there's no questions here. This is just telling you the breakdown of 1 coin, heads or tails. Now 2 coins, 3 coins, there's actually a pattern that emerges, but that would be the breakdown of different possibilities. If you flip a coin twice or flip 2 coins once, that's the same thing. You could they might both be heads. Maybe they're both be tails. Maybe the first one's heads, the second one's tails, or the first one's tails and the second one's heads. The order actually matters. So 2 pieces of information here. 1, the order matters. And also, when we say flipping 2 coins, I'll say flipping 2 coins is the same as flipping 1 coin twice. It doesn't seem like a big deal, but it has confused people in the past. You could look at the two events independently, or you could look at them collectively. You would just say, I mean, just visualize it. I mean, if you have coins, you can just do it. You have like I have to flip a coin twice, but I only have one coin. So flip that one coin twice. But if I have to flip a coin twice, I could just use 2 coins and flip them both at the same time. And it would amount to the same thing. It's the same idea for 3 coins. Flipping 3 coins is the same as flipping 1 coin 3 times. Rolling a die, the outcomes are 1 through 6. I put a little image of dice there just because, I mean, most people know what the dice is, what dice are, but the die thing, it's not always the case that people know the singular of dice is die. All right. So I figured I'd clear that out. Otherwise, it seems pretty terrible to have that in the notes. And this is the unwrapped die. Okay, so this is what all the sides look like. If you were to kind of fold this back together, it's called a net. You fold it back together, you would get the die. But this gives you the sense of what the outcomes are. You could have, 1 dot, 2 dots, 3 dots, 4 dots, and so on. Each corresponds to a numerical value. So we just say the numbers 1, 2, 3, 4, 5, and 6. The cards. The cards are probably the trickiest thing because not everybody plays cards. So, like maybe the suits, the clubs, the diamonds, the hearts, and the spades, but maybe you don't know, like which card is more powerful than another card. Like it's for those of you familiar with blackjack, this isn't that. So we don't assume that the jacks, queens, and kings, the JQs and Ks are worth 10 points. It's not like that. All right. That's a particular game. What we do assume is that all J's have the same value. It's just not a numeric value. Think of it as a variable. Each one of those J's is a J, so they're all equal to each other. All right. But they don't have a number associated with them. Same thing with the A's, the Q's, and the K's. All right. They're equal to each other. All the Q's are equal to each other. They just don't have a number associated with them in all cases. The breakdown at the bottom there, just a refresher on prime numbers. This is actually just a list of a few of them, but basically the definition is any number that is divisible by only 2 unique values. All right. And those values they have to be unique. When we say unique, we say different from one another. Right? The classic definition of unique. But people don't always know that. So for example, the only way you're going to get to a 2 is if you multiply a 1 and a 2 in either order, assuming that you're only able to work with whole number values. All right. So I guess I should throw that in there, any whole number. I sort of take things for granted sometimes because we don't bother with integers either. So no negatives here. Just whole numbers. Any whole number that's divisible by only 2 unique values. So I'll just do a couple. The only way you're getting to a 23 is by taking a 1 and multiplying it by 23. All right. 2 is the only even prime number. Everything else is an odd number. That's kind of a quirk of the universe, but it's kind of cool. And it's sort of the exception that proves the rule. But the reason I bring this up, it's not a number theory course. It's probability. But sometimes a question will say, what is the probability that a card selected at random is red and also a prime number? All right. So in that case, I don't want you to get thrown by the fact that we're dealing with prime numbers. All right. Perfect squares, perfect cubes, and perfect fourths. They come up from time to time. So I figured I would just make a list of that. There's really nothing too crazy there. In order to be able to handle probability questions, we have to understand the logic of it. I mean, I want to be fair. you can totally get questions right related to probability and not really know much about logic or Venn diagrams. Some of them are just easy enough that you could just kind of reason it out. If I say that I'm going to roll the die twice, so I go to my sample space of dice here, and I want to get a sum of 2. I'll keep it very simple. It's very, very basic, because I would just look at it and say, okay, well, what pair of values will add to the number 2? And how many pairs are there overall? 36. So there's one, I think I said 2. I mean, there's only one value, the one pair of values that are going to add to 2. And there are 36 pairs overall. So for example, the probability of getting a sum of 2 would be 1 out of 36. This would be the number of pairs that add to 2. Thad. I merged that and add, in case anybody was wondering. That add to 2. Number of pairs in total. All right. So just a quick example, that in terms of logic, I mean, the logic was there. It's just, it was happening behind the scenes. Sometimes we confuse logic with common sense, right? When somebody says or does something that is against what you would consider sensical, we say, oh, well, that's not a logical thing to do. That's not reasonable. That's another way of saying it. Logic and reasoning go together. But sometimes it's not that it's illogical. It's just, it's not something that you would expect or something that you would do. All right. So it's an unlikely outcome, but the logic may be there. I mean, you could logically justify pretty much anything you want, even something awful. So, logic is not, it's only the beginning of wisdom, as Spock would say. It's just a tool to analyze scenarios, but you use your best judgment when push comes to shove in real life. But in math, we tend to stick to the logic because it's a framework that allows everything to kind of, fall into place. Right. And if you don't have a basis for your arguments, your reasoning, and most of the time that's logic, you really don't get too far too fast. All right, so we're going to talk about just basic logical connectors. One is the conjunction, and another is a disjunction. We also have an implication, but we'll get to that down the line. I would say the implication is when things start getting difficult. All right, so the first two, conjunction and disjunction, they're really not that bad. They're actually, in a lot of cases, really simplistic. In some cases, they're complicated in terms of what you have to write down on paper, but in terms of setting it up and doing the calculations, it could be pretty easy. All right. So we have a conjunction is denoted by the I'll call it an upside down V, but I like it. I like to kind of think of that as an almost A. It's basically an A without that little crossbar here. It's almost an A. The reason why I like that is because that symbol represents and. The one that looks almost like an A is the and. All right. So that always worked for me. The other one is or. I'm still working on something creative for that. Yeah, it's just the one that's not the one that looks like an A is the symbol for or. And then the sideways arrow is, well, we say implies, but it's really an if then. I mean, they both mean the same thing. All right. So if something happens as a premise, what would the conclusion of that be? All right. So that one's the tricky one because the logic of it says that the the P part of it, P implies Q, the P part of it doesn't always have to be true to give a true outcome. All right. So that's where people get jammed up. But for today, we're just going to focus on the conjunction and disjunction. And you also see the not A. And I have a couple of examples that are a little involved, but I'll take you through first the breakdown here. The intersection of two sets denotes the elements that the sets have in common, or the overlap of the two sets. Right. That's what a Venn diagram is really telling us. So when I look at this diagram here, I have two variables that I'm working with, or two events, right? But those events often represent a random variable. All right. One is set A and the other is set B. That area of overlap, that is the set of A intersecting with B. All right. So this is an intersect. All right. That's the case of and. It's slightly different notation. I used an almost A up top, pointy A, but now it's still the same idea where you could make that into kind of like an A by putting a crossbar in there. That's how we know. Well, that's my mnemonic device for remembering that that's the and. All right. This other one is the union. That's the case of or. All right. So the union, when you take the union of two sets, it merges the two sets into a bigger set. Right. So if I have the set of A and the set of B, I would say, okay, well, let me take all of my A's. This would be my set of A's. That's all of them. And then let me take my set of B's. Putting these two sets together would give us the union of A and B. Let me fix that. It went a little outside the lines. All right. But if I want to combine these two sets, I got to be careful, because if I say that I'm going to take my set of A and add to it the set of B, well, that's not necessarily the union of A and B, right? Because you have that overlap here. All right. Again, that's the and. That's the cases that coincide between the two sets. So I don't want to accidentally count those twice. The way I would look at this is by saying that I would take the set of A and B and add them together, but then I would subtract the overlap, which is A intersect B. All right. So this is, the first one is not necessarily A union B. The other one is. If you take those two entire sets, all of the yellow, all of the blue, add them together, if there is overlap, we'd subtract that off because we double counted it. All right. So let me show you in a little bit more of a meaningful way here. So if I take, this is all of my A's, you see I've counted the overlap already. All right. That part in the middle, that's been accounted for. So just by looking at set A, I'm getting part of set B. Now, if I go in and count all of set B, I'm also counting part of set A. I'm double counting that overlap. I'm double counting that, and that would be a problem. I would get an overestimate of the probability. All right. So I'll take you through a more practical example in a little bit, but this is a really important foundational concept. It gives us something related to the addition rule, which we'll get to probably not tonight, but we'll get to it soon rather than later. Question?
Hi, so basically whatever number that's shared between A and B, just use it only once.
Exactly.
Okay,
Perfect. Very good.
thank you.
All right. So looking at the complement, that's actually pretty, I'll say easy, but people tend to neglect the area outside of the circle. So we got to be careful about that. If I'm saying that this circle here is set A, all right. So that this whole circle here would be the set of A. Then everything else would be not that. All right. I'm only talking about sets A and B, but maybe there's a set C, D, set F is set, like however many sets you can think of. I mean, it goes beyond just the alphabet. I mean, you can get into subscripts and say set A1, set A2, it can get complicated. But what we're looking at is everything except for set A. So everything outside of the circle. So this red area here, that's the set of not A. Anything else that can occur. All right. It's like Superman 2. When he's at the Fortress of Solitude and they're trying to take his powers away, he goes into the booth and all the radiation, the red sun of Krypton radiation, engulfs the people who are outside the booth, but he was safe on the inside. That's really what's happening here. It's the exact opposite of what they expected to happen. Superman 2, classic movie. I recommend it if you haven't seen it. So on a Venn diagram, we could have, a lot of different possible outcomes here. The directions say shade the regions corresponding to A union not B. What I like to do, just kind of off on the side. I mean, this doesn't really benefit. Well, it'll benefit you, but it's not something that's practical necessarily for you to do. But what I like to do is just kind of off on the side. I address each of these ideas individually. So I'll create this diagram, or I'll recreate it. Get rid of the shading. The circle thing is kind of an issue. It used to work. Well, I guess I just have to, do it that way. So I have a Venn diagram, a blank one that I could use repeatedly. So I'll just kind of pull this off onto the side and copy it just so I have it. All right. So this is the actual Venn diagram. If I'm just looking at A, all right, here's my set of A. This is B. I would just be talking about this region here. So that would be my set of A. So that's addressing the first component. So I just kind of put this off on the side for a sec. All right. Then what I would do is take care of the second part. The not B. All right. Not B is everything outside of B. So I would look at this and say, well, I got to start shading here. Everything outside of B is what I'm looking for. Actually, let me use a thinner. Takes a little longer, but it's a little bit more accurate. So this would be not B. All right, everything outside is your not B. What I would then do is merge my two diagrams. And that would be the overall figure that I would be looking to reference. And it's probably better off on the side here. All right. So what this is telling me, or at least, I'm sorry, what the union symbol is telling me, this one right here, is that we're merging the two sets. All right. So I would want anything that's A along with anything that's not B. All right. So it could just be A, it could just be not B, or maybe it's both at the same time. Like this this double shaded region here, that's both A and not B. Right? That's fine too. We're taking anything that has any shading whatsoever and including that in our final diagram. All right. So that would be everything outside of this this white area here. All right. So yeah, it's not the easiest thing to draw, but I'll give it my best. You know, some people can kind of see it right away, just based off the logic of it. I would say that takes a fair amount of experience. It's not always the easiest thing in the world. So, you know, like using kind of scratch work on the side can be a good thing. I mean, it definitely is a good thing. It's just not always necessary. You know, if you can see it right away, then you're good. If not, then you have a little work to do. Number two is made up of the same ingredients as number one. Right, so you'd have, oh, not that. So I had my set of A, and I think I could still snag my set of B here. Kinda. Put that back I'll put it here for a sec. You know what? Paste it. Just need the outside. Actually, I also need the A, but all right, kinda. All right, so I got my A and I got my not B. All right, so I would still merge the two sets, but this time I'd be looking for overlap. So I'd put the two together just the same way I did before, but this time I'm not going to make the same mistake and actually leave it there. These are the two ingredients. We have A and we have not B. Putting them together allows you to determine the union or the intersection. All right, so you get two for the price of one. So it would actually be the same diagram. It's just what we were pulling for that from that diagram would be different. All right. So in this case, by the union, I'm sorry, by the intersection, I'm looking for overlap between the two sets. All right. So the overlap only happens. I mean, it would have been nice if when I put the yellow and blue together, it made a nice green instead of made an ugly green. But it's really just talking about this piece right here. All right. So that's what I want to shade in because that's the case of A intersecting with not B. All right, but it's the act of merging the two sets together that helps you understand that. And like I said before, some people can just look at it and say, oh, okay, that's what it's going to be. You know, it's along the lines of creating a definition in your mind and saying, okay, how would this play out? You know, doesn't work for everyone, but if it does, it's a good thing. All right. The next one, not A union B. So what that's doing is it's taking A union B, which we have up here, and just saying, okay, not that. Right. So the A union B is the merging of the two sets. So I could steal my graph from before, but I'm not gonna. I'm just gonna do it again. I'll take this. I'm just gonna clean it up. Get this out of here. We don't need this. So we get yellow here. So if I put the two sets together, I get anything that's shaded. All right, so this set here is A union B. All right, not just the overlap, but all of it together collectively. All right, so what I'm saying in this case is, well, I don't want that. I want everything that's not shaded. So that's going to be all of this stuff here. All right. And so that would be my not A union B. So the union of A and B is everything that's contained within the circles, even the overlap. Not that would be everything outside. Now, number 4 is probably the most interesting one, because it's actually going to give us the same outcome that we had for number 3. It's just, it's a different expression. All right. So we work with a logical process called De Morgan's laws, which allows you to negate a union and make it into an intersection. So I'll show you that, because we know what not A looks like. I'm just going to steal this. So this is the set of A, what I have in blue. I don't want that. I want not A. So let me get rid of this and shade anything that's not in there. I'm just going to save this real quick. All right. So anything that's not contained within A. All right. So that's not A. For not B, same idea. I'm just going to tuck it down over here. Same idea, except we're referencing the B. So anything outside the B circle. Circle being the word of the day. Circle. As in what we've been drawing over and over again. All right, so this is a case of not B. Now, this symbol here again means that you're looking for the overlap. All right, so what I would do is I would take my two sets and put them together, and yellow and blue makes green. So I'm just looking for anything that's quote unquote green. All right, so that would be anything that's outside of the two interlinked circles. All right, so it's really the same thing, not the yellow, not the blue, but the quote unquote green. Because I mean, this is a glorious looking green here. This is like vomit green. Actually, that would be like unhealthy vomit green. Well, I guess if you're vomiting, you're probably not healthy, but you never know. Or maybe you're really healthy. Who knows? Those cleanses that people do. So anyway, that's giving us the same outcome. It was a different road to get there, but it gave us the same outcome. And what that tells me is that if you know two things that are equivalent, so numbers 3 and number 4, if you know that they're equivalent and one instance is easier to work with, you go with that because it'll work both ways. All right. So I mean, it's tricky. Venn diagrams are always kind of like mind bendy. And I know that I mean, the software makes it easy for me. It's not necessarily easy for everyone else, but hopefully you kind of see the idea of the merging of the diagrams. All right. I don't think I need this anymore. Oops, that's not a lasso. All right. And we'll come back to Venn diagrams, but we're still in the formative part of the unit. So we have to cover more basic concepts first before we can start putting it all together. On page 22, we talked about sample spaces, but I would imagine, and it's not really much of a leap, that you would probably not want to have to list out every possible outcome in a data set in order to know, or a sample space, I should say, in order to know how many elements make up that sample space. Right? It's just a question of being efficient. Right? So if I know that there are 36 outcomes in a sample space, and I'm only interested in one of those outcomes as a success, then 1 out of 36. But I wouldn't want to have to list out all the outcomes for 2 rolls of a die in order to figure that out. All right. So we come up with a relationship. The first part of it has to do with the coin. You'll see in a little blurb here, 1 flip yields 2 outcomes. 2 flips leads to 4 outcomes. 3 gives 8. 4 gives 16. We want to know what'll happen if I had any number of flips. All right. The idea is to figure out the relationship for the cases that we do know, so that we can figure out cases that we don't. All right. It does appear that we're multiplying by 2 every step of the way here, but really what we're looking at are powers of 2. So 2 is the same as 2 to the first power. All right. That 1 as the power comes from the number of flips, because 4 is the same as 2 to the second. 8 is 2 to the third. 16 is 2 to the fourth. So you ask, okay, well, what would be n? Well, it seems like it's 2 raised to the power of whatever the number of flips is. So this would be 2 to the nth. All right. So if I had, for example, 20 flips of a coin, I could expect 2 to the 20th power outcomes. Now, sometimes the number's so big that you get an overflow. This isn't one of those cases, but you just be mindful of that. If you get something that's so massive as a result, you're better off leaving it as an exponent. And even this is kind of borderline. I'd rather write 2 to the 20th power than what is this, 1,048,576. All right. When you're doubling, the numbers increase pretty rapidly, but they don't increase as rapidly as if you were consistently multiplying by like 100. You know, so doubling versus multiplying by 100 is you're gonna get to large numbers, but not as quickly. All right. When you roll a die, a single die, you have 6 outcomes. 2 dice, you have 36. 3, you have 216. Right, and that 6 comes from 6 to the first power. 36 is 6 to the second power. 216 is 6 to the third power. The next one I think is 1296. Let me just double check. Oh, 864, not even close. Oh, why did I multiply by 4? Nobody knows. Times 6 is what I should have done. It is 1296. Just I got it my own way there. 6 to the fourth power. Again, we have that relationship. Number of rolls gives you the power. So we're looking at n 6 to the nth power as the number of outcomes for n rolls of a die. All right. So for example, 20 rolls would be 6 to the 20th power. And that's where, I mean, you get something really massive. If you look, you'll see that they'll give you the really expansive value, or they'll give it to you in scientific notation. When you compare the two, it's like, which one's better than the other? They both look pretty awful. So in this case, I would leave it as 6 to the 20th power outcomes. All right. So the general formula that we come up with, you know, because we're not always going to be talking about coins and dice, for whatever scenario you're dealing with, you could always say the number of outcomes per trial raised to the number of trials. All right, and that'll give you the total number of outcomes in a sample space. All right, sometimes it's tricky to come up with the number of outcomes per trial, but if you can, all you'd have to do is raise that to the power of the number of trials. This only works for what we call independent events. So we're still keeping it kind of basic at this point, but it will get a little bit kookier as we go forward. The last thing I wanted to talk about is the addition rule. And there are, I mean, I have all the examples here, but just a quick refresher. When we talk about A union B, we're talking about the set of all values of A merged with the set of all values of B. I'll put the A's and B's in here in a second. So this is A, this is B, and this is the overlap. A intersected with B. All right. So if we want to find the probability of the merged sets A union B, one way to do it, there's a couple ways, but the other ways are more complicated, a lot more complicated. I could take all of my set of A, so all of the yellow, I can take all of my set of B, all right? So both of those full circles, but then subtract off any overlap, because when they overlap, I have equal parts yellow and blue. That green area gets double counted. I have blue accounting for it, but I also have yellow accounting for it. right? So I would just subtract that off. So I would subtract off the probability of A intersected with B. All right. So we interpret this union symbol as an OR, and this intersection symbol as an AND. All right. So if I want to find the probability of either of two events occurring, I would add the probability of each one individually and then subtract off any overlap. All right. I'm just going to take you through one example. If memory serves, one of these examples is bad. So I'm looking at number 2, and I think that might be the one, but I'm not 100% sure. Oh, actually, number 1 is bad too, because that's only good for in person. All right. So actually, let's toss these two. I'll just go right to the card problem. A card is selected from a standard 52 card deck. Find the probability of either a 7 or an ace being selected. All right. So probability of a 7 or an ace would be equal to the probability of getting a 7 plus the probability of getting an ace minus the probability of a card being both a 7 and an ace. All right. This is an instance of no overlap. Oh, that was the other typo. This is a good one for somebody. These diagrams shouldn't have the circles in them. Like you should draw those yourself, because they don't always overlap. All right, now if you're not as familiar with a deck of cards, you may not pick up on this, but you could always refer back to that page, the previous one. Oh, where is it? Page 22. This is my deck of cards, this whole thing here. I have my set of 7s. That's all of these cards. And I have my set of aces. There's no way you could have a card that's both a 7 and an ace at the same time. They're two different cards. All right. Now you could have a 7 card that's red. You know, like there's a couple ways that could happen. That would be a case of overlap, but you can't have a 7 and an ace at the same time, right, on a single card. But again, if you don't know much about cards, you might not pick up on that. But here we have no overlap. All right. So in my Venn diagram, I'd have a circle for A and a circle for B, but they wouldn't be intersecting one another. All right. Let me see if I can fix this. All right, so there's no overlap between the two sets, which means I don't have to subtract anything. So this is my A, this is my B. All I would do is just add the probability of getting a 7 with the probability of getting an ace. All right, so this part becomes irrelevant. So I'm looking at 4 out of the 52 cards are 7s. 4 out of the 52 cards are aces. So that's 8 out of 52. All right. I mean, you could put it in decimal form, but it's pretty clean in fraction form. But the decimal equivalent, you'd have to round it. It'd be about 0.154. So approximately 0.154. All right, so let me actually just show you one real quick where there is overlap. Probability getting either a 7 or a red card. So probability of 7 or red would be probability of 7 plus the probability of red minus the probability of 7 and red. All right. So you can look at it the same way we did the previous one, but this time you can have cards that are both 7 and red at the same time. So now this is relevant. All right. So I'd look at my set of cards or my deck of cards. I know that there are 4 cards that are 7s, and there are, well, half the deck is red, so 26 out of 52. But then I would subtract off any overlap. All right. And so people go about this different ways. You'd say, all right, I'll take all my reds and then I'll take any 7s that I haven't accounted for already. And that would get you your final answer. But you know, this is the standard way of doing it. You can deviate as long as it makes sense. All right. But there are 2 cards out of the 52 that are red and 7. All right, that was the 7 of hearts. I'll do it in red. 7 of hearts, 7 of diamonds. All right, those are the 2 that are also red. So I'll take you to the diagram in a sec, but this would give us computationally 28. It's going to be 4 plus 26 is 30, minus 2 is 28. Common denominator out of 52. And we saw before, maybe we don't want to go decimal form on this, but if you did, you'd get about 0.538. All right. So in this case, my A and my B do overlap. Actually, you got an idea. All right, my A and B's do overlap, but I still want the union of the sets. All right, so I'm looking at all of my A's and all of the B's that haven't already been accounted for. That would be the union. But if I do account for all the B's, I'd have to subtract off the overlap. Oh, I normally do that in blue. All right, so that's where this is coming from. But let me just take you to the diagram real quick. All right, so if I'm looking at the deck of cards and I'm talking about 7s and reds, here's my set of 7s. All right, now if I want my set of reds, that would be all these cards. All right, now if I count up only the unique values, I'll get to 28 cards. All right, because I would go here and I'd say, all right, well, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26 cards. Now I would just have to account for anything that's still highlighted that hasn't been accounted for. So I'm at 26, 27, 28. I would not count these cards a second time. All right. I would only count them the one time. Otherwise, I'd get an overestimate. All right. So that's the introduction to probability. It gets trickier, but if you stay on board, you know, and do all the things that you need to do, then it'll never get that bad, because this course is not called probability, it's called statistics. So we only learn as much probability as necessary in order to understand the statistics. If you were to take a course on probability theory down the line, that's more involved. All right, but this is the basics, the bare bones. All right, so I'll send out the we're going to pick up with page 26. Well, yeah, I want to take you through page 26 next time, so I won't put that on the video list. We'll skip that, but then you'll look at some videos for multiplication rule and conditional probability. All right, so I'll send out the to-do list in a little while. So be on the lookout for that. And it was brought to my attention earlier, if you missed it, that sometimes these notes don't update right away. So give it overnight before you, if you're looking for the notes, you can take a look on that. Question.
Professor, do you mind going up to 24? I need to copy that.
You got it. Page 24. There it is.
There you go. Thank you.
No problem. So at this point, I know there's another question, but let me stop the recording real quick.